Hello, welcome. This is an informal little talk that I give about what is Node.js, as you can see. I'm Riley, they, them, if you please. And this is a question with, it's a question with a one-sentence answer, a one-paragraph answer, and the rest of the talk. Let's get started. So the short version, the extreme short version, Node.js is a native runtime environment for JavaScript. Okay, what does that mean? Well, the one paragraph answer is that it lets you run JavaScript outside of a browser. JavaScript running inside of a browser has a bunch of limitations put on it. For example, it can't go poking around in your operating system. It's what we call sandboxed, which we'll talk about later. So Node.js is basically the part of Chrome that runs JavaScript that was scooped out and made into a standalone interpreter. So if that answer satisfies you, we're done here. Carry on. Go on with your day. But if you want to dive deeper, if you want to dive much deeper, we'll need to go back. We'll need to go back to the very beginning. So first off, this is a disclaimer. Everything that I talk about, this is a gross oversimplification. Do not quote me to anyone, much less someone who knows what they're talking about. It is for entertainment. And yeah, okay. So we begin with the transistor. You can see the major stages of transistor development: the vacuum tube, the solid-state transistor, and the Minecraft transistor. So what is a transistor? Well, it's basically a switch that's controlled by electricity. In other words, it's either conductive or it's not conductive based on another electrical current. And with these bad boys, we can build logic gates, and those logic gates can perform logical operations. They can perform math operations. They can do all kinds of very fancy things. And every modern computer is made out of billions of these things. So there are a few first computers that I could have talked about. There's the ABC. There's Colossus. There's the Z3 or the Z3 if you prefer. ENIAC is attractive for a couple of reasons. For one thing, it was what we call Turing complete, which isn't a topic we're going to spend a lot of time on, but basically you can compute anything that is computable. The thing with ENIAC, so it was built in the 40s, it was built during World War II, and it was designed for ballistics calculations, but what it ended up being mostly used for was nuclear weapons simulations. So that's cool. That's good. You programmed it, and you can see this in the picture. You programmed it, and I'm putting that in air quotes, by these switchboards. You programmed it by physically rewiring the machine, which was a process that took days and it took weeks to test. So this was a good start. This was a good start, but it was pretty clear that we would need a better model for programming these things, which brings us to the next major computer that we'll talk about. This is the EDSAC. So the EDSAC is the first computer, or at least the first computer I know of, that you could program by feeding in paper tape with punches made in it. The paper tape was originally designed for telegraph operation. And yeah, so it was built in Cambridge in 1949. And how did that work? How did this punched paper approach work? Well, each paper had a series of holes, and the number and positions of those holes indicated a number. And each one of these different numbers was something that we could call an opcode. And these opcodes would say something like, take whatever values in this part of memory and whatever values in this other part of memory, and add them together and put it in a third part of memory. One of the things about EDSAC, though, was that it had to sort of justify its existence. It was built under the guide of Cambridge's math department, and so basically it had to be useful. It had to be useful for mathematical applications. A lot of really early mathematical number theory work and so on was done on EDSAC, including finding some of the biggest primes, too big to reasonably figure out by hand. So, because it was designed for non-programmers, it had to have a relatively friendly language. This was an incredibly primitive form of assembly, which there are some computer file videos about this. They'll go into it in more detail than I can. But you could just write arbitrary data. You could write arbitrary data on this whole paper. You could feed it into this machine, and it would basically do what it was told. You didn't have to physically rewire it to get it to run a different program. You just fed in different bits of tape. So this programming language that you fed into the EDSAC was called assembly, as I said. It's the thing with assembly code is that it's machine specific. So if you write your code in one machine's assembly, you can't really port it to another machine without rewriting the entire thing, which is, understandably pretty prohibitive. This is a problem that would persist, basically until Intel took over everything in the 90s. We'll get there. We'll get there eventually. But for now, you have a bunch of different computers. Each one has a different assembly. You might even break backwards compatibility between different computers on the same line, which is no good. So that brings us to the first solution to this, which was compiled languages. Now this handsome devil is the PDP-11. It's beautiful, isn't it? And this is what C was written in. So C was not the first compiled language, not by a long shot. There was Algol, which was written in the late 50s. There was COBOL, which was also written in the late 50s. There was Fortran. As I say, there were a few compiled languages before this. C's popularity had to do with, it came out of Bell Labs. It's the first instance of this lie that we'll be visiting and revisiting over and over again. Write once, run anywhere. So the idea is that you write your C code once, and you feed it to a program called a compiler. So an assembler takes your written assembly instructions and it converts it into a native machine code. Well, a compiler does the same thing, except the representation for a compiled language is typically much higher level. And yeah, C was a high-level programming language, certainly by the standards of 1971. So the idea is that you have a whole bunch of compilers, or you have one compiler which has a whole bunch of different endpoints. You write your C code once, you compile it to whatever targets you want, and there you have it. You have code that you wrote once that can be effortlessly, and I want to put effortlessly in huge air quotes, effortlessly made to run on any number of devices. Now, unfortunately, different machines have different capabilities, especially then. They had different memory layouts, different clock speeds, different clock accuracies, different word sizes. It was kind of the Wild West at this point. How big is an integer is still a problem that C programmers need to worry about. So, as I say, this was the plan, write once, run anywhere. It turns out that plan doesn't work out so well when you bring it into the actual world. Not that it doesn't work most of the time, because it does, but because there are these pesky edge cases that are hard to get rid of. Now, let's look at another approach to solve this problem. So, a compiled language, you write your code, you hand it to this compiler, the compiler turns it into native machine instructions, and you just run those native machine instructions. And that process can take a while. That compiling process can take a while. Now, an interpreted language, and for this we're going to use BASIC. BASIC was developed in the 60s. Again, it is by no means the first interpreted programming language, but it was a very popular one, especially in the 80s in the home computer boom. You can see a Commodore 64 here. No, that is not true. You can see a Tandy 1000 here with a grumpy-looking cat. And yeah, so BASIC was an interpreted programming language. And the advantages of interpreted programming languages were really obvious, even really early, even with very limited machines. The advantages of an interpreted language were obvious. So, basically, instead of a compiled language, where you take your code, you convert it into native machine code, an interpreted language is itself a program. It has a program called an interpreter. And that interpreter is like a little robot. It eats your instructions one by one. It reads down the list of your instructions, and it sort of does what it's told step by step. So, interpreted languages are typically a lot slower. That interpreter has some overhead. It takes time to read your code or read your instructions and then execute them, time that a native machine program doesn't. But it doesn't have any compile times. And in practice, not necessarily in theory, but in practice, the language can be more user-friendly. When you're writing BASIC, you're not really that worried. You're not worried about types. You're not worried about pointers. You're not worried about native machine instructions. You're not worried about all sorts of more advanced topics that writing assembly in C would force you to care about. But yeah, so the main con, after all of those pros, the main con is that they are slow. That brings us to Java. Okay, so Java's kind of a contentious language. People like to bash it a lot, and some of those reasons are good, and some of those reasons are not good. One of the things about Java is that it wasn't innovative. None of its ideas were brand new. What it did was it popularized a lot of ideas that had been kicking around for a while. Things like garbage collection. The garbage collection had been around since at least the 60s when it was invented for Lisp, but Java popularized it. And another thing that Java popularized was what's called a bytecode interpreter. And so this is sort of a best of both worlds approach. Instead of writing your code in a high-level language and then interpreting it line by line, what you do is you write your code in a high-level language. You convert it to an intermediate bytecode, which is a low-level instruction set that's not tied to a particular architecture. It's tied to, it's just tied to its own interpreter. And then you can port that interpreter to different architectures, and the same bytecode will run on each one. Java is the first programming language I know of that largely got popular because of a huge marketing push. Now, one of the things about Java is that it was going after C, and it was going after C++. C and C++ were the standard. They were very high performance. They compiled to native machine code. And the first version of Java, Java 1.0, was simply not fast enough. This bytecode interpreter was fast. It was a lot faster than older kinds of interpreters that were still kicking around. But it wasn't fast enough. It wasn't C++ fast. How do we make an interpreted language C++ fast? For that matter, is Java an interpreted language? Because, yeah, okay, it has an interpreter. It has a program that interprets it at runtime, but it also has a compiler. It compiles your code into a low-level bytecode that then gets interpreted. Well, there was one other innovation that Java didn't originate, but it did popularize, which was just-in-time. Now, hold on a second. This is going to require a little bit of explanation. So there's this short. There's a series of shorts called Wallace and Gromit, which you're looking at a still from. In the second short, The Wrong Trousers, you can see the penguin here, whose name is Feathers McGraw. He's the villain of the short. And down here on the bottom left, we see the dog Gromit, who is the hero. And there's the useless human, Wallace. Now, they're in a train chase. Feathers McGraw is trying to escape with a stolen diamond that he has in the bag there. And Gromit is trying to catch him. Feathers here forces Gromit's train onto another track that's about to run out. So what does Gromit do? Gromit grabs a box of track and starts slapping it down in front of his train as fast as he can. This is essentially how just-in-time compiled languages work. So the idea with a just-in-time compiled language, the idea with Java 2, was we're going to start running the code like normal with this interpreted bytecode. But as it's running, we're going to analyze how it performs. We're going to say, oh, this function gets used a whole lot. This is performance critical, or in other words, it's on the hot path. And so what we can do is we can compile this function into native machine code. So we have a compiler that takes your Java code, it turns it into Java intermediate bytecode. We have the Java interpreter, which interprets your Java intermediate bytecode, and then compiles it into native machine code while the program is running. So I ask again, is Java compiled or is it interpreted? It's kind of a gray area. It's kind of both. There's this idea that some programmers have that it's an all or nothing thing, that a language is either compiled or interpreted. And in fact, almost all languages are, the answer is both. They are both. So one of the other lies about Java was, again, this idea of write once, run anywhere. This is the first time where I heard this term used in so many words. Write once, run anywhere. And it's not any more true for Java than it was of C. They patched in some more of the holes. They patched in more of the places where incompatibilities would come up. But you can only go so far. And it feels like every generation a new technique is flouted as a solution to this problem. Right now we are in the containerization, Docker, Kubernetes era. And again, you can get close. You can get real close, but you just can't get 100% there. So finally, you might be wondering, what does any of this have to do with Node.js? Well, we finally got into JavaScript. Congratulations. Behold, the beauty that is Space Jam's website from 1996. This is the headspace that I want you to get into. Now, JavaScript was written by one dude in 10 days in 1995 for the Netscape browser. The internet was a simpler place, a better place. You had your scrolling backgrounds, you had your spinning GIFs, you had your auto-playing music, and JavaScript had a very different role in 1995 than it does today. It was used to add just a little interactivity to your otherwise static website. Maybe a little animation, Maybe it would make it so a form, you wouldn't have to reload a form. It had to be optional because not everybody was using Netscape. And performance wasn't a huge deal. The internet was slow. It was very slow. The JavaScript was simply not used enough to be a real bottleneck. Let's move on. Let's move on to the browser wars. So during the browser wars, JavaScript became a battleground. JavaScript performance became a battleground. And so all of these optimizations, all of these techniques that we've been hearing about that were invented much earlier and popularized by Java were brought to bear. Now, Chrome is this 800-pound gorilla that dropped into the scene. And part of the power of Chrome is the V8 virtual machine. The V8 virtual machine is the JavaScript interpreter in Google Chrome, and it has tons of very clever optimizations. Again, we're not using JavaScript for what it was designed for. It's kind of wild that it's even possible to write a just-in-time compiler for a language that's as dynamic as JavaScript is. I mentioned the Sandbox earlier. Let's talk about Python for a second. So Python is another interpreted programming language. It has an intermediate bytecode. It doesn't have a just-in-time compiler, at least not the normal version. The Python interpreter has full access to your computer, your operating system, your file system, and so on. Now imagine if every script you ran in the browser had that kind of access. That would be terrible. That would be very bad. So browsers run JavaScript in a sandbox, only giving it access to, well, the things that are the purview of the browser. When the browser asks you for permission to know your location, for example, that's because JavaScript can't just access your GPS directly. It has to request access to that through the browser. So the sandbox sort of fundamentally limits what JavaScript can do. JavaScript can only do so much because it's running in a browser. So the thinking went, why not remove the sandbox? And now we finally have gotten to Node.js. So Node.js is the V8 virtual machine from Google Chrome. The developer took the V8 virtual machine out of Chrome, attached a bunch of stuff to it, and that stuff includes access to the operating system, access to the file system, access to the terminal, access to basically everything. And so now you can run JavaScript locally outside of a browser to your heart's content. And that's it. That's the story. That's basically the entire history of computer science compressed into this quick little talk. So, thanks for watching. I have a Patreon, I guess. You can like and subscribe, I guess? Question mark? There's a bell, I guess. I don't really care. I don't really care. But if you like what I do the regular things, do all that stuff, and I would appreciate it. I also offer mentoring services. So if you liked my spiel, if you thought it was a good explanation, you can go ahead and shoot me an email at the email on screen. We could do a free consultation. We could do something like that. Thank you very much for watching. Fight the power. Black Lives Matter. Stop Asian hate. And trans rights. Free Palestine. Thank you and good night.